Welcome, everyone. Welcome to the, I don't know exactly how many Vernon lectures we've had since 2006. I think we started, so this is the 2004 Spring Vernon Lecture. And before I introduce the speaker, we have a little bit of an announcement to do. We have a new program that's been initiated by the Mount Cuba Foundation called the Mount Cuba Scholars Program. And Rob Lancaster, who's the president of the Delaware Astronomical Society, is going to introduce our scholars and talk a little bit about the program before we start the lecture. So come on up, Rob.
Good evening, everyone. I'm Rob Lancaster, and last year the Mount Cuba Foundation asked me to design and set up a program for small groups of high school students to participate in actual research in astronomy. And here they are right here. We're calling it the... Absolutely. We are calling it the Mount Cuba Scholars Program. Through this program, they have an excellent opportunity to work closely with University of Delaware graduate students who are sitting right over there. And right there, sorry, and right there. Absolutely. And they're going to have these folks as mentors to help them in their research. The graduate students share their knowledge and experience with the students, inspiring their budding interests in the fields of science, technology, engineering, and math, particularly in the field of astronomy, which is close to all of our hearts. We love astronomy. Over the last several months, this inaugural group of students has been working very hard on their own creative astronomical research projects. Catherine Hart is working very hard with her mentor, Kaylee Grace, who is observing from Chile right now from her seat, which is really exciting. Right? And as I was saying, Catherine and Kaylee are studying eclipsing binary stars. She's studying periodograms of various stars to determine the periods of their orbiting companions. Yassine Koken is working with his mentor, Zach Savory, who's back there, great, to apply his programming knowledge to Python scripts for studying exoplanet data. Rushil Patel is working with his mentor, Henry Sanford Crane, who's right there, to find white dwarf stars that might have exoplanets. They are analyzing the data from the Montreal database to study for likely exoplanet candidates and hope to request time on the James Webb Space Telescope to do follow-up observations. Absolutely. Yeah, that's exciting. We are hoping to continue to develop and expand this program into the future to help future students and inspire the next generation of astronomical researchers. Thank you very much.
Thank you, Rob. So tonight we have our guest speaker is, and I'm going to try to say this right, he taught me how to say his name, Xavier Prochaska, okay, who is he's an astronomer at UC Observatories, which is part of the University of California. He's a graduate of Princeton University. He got his PhD at the University of California, and he was also a Hubble Fellow, a Hubble and Carnegie Fellow, which is a very prestigious award to get. And his interests are dissecting the light emitted from distant sources, which sounds very mysterious, but he's going to show you all about it tonight. And the reason he likes to do this is because he's also interested in determining the physical processes that drive the formation of the universe. So that's very exciting. And the other thing I learned about him when I was Googling him before yesterday, he is becoming interested in oceanography and pivoting to actually from astronomy to becoming an oceanographer. So I thought that was really cool. That's very brave to change subjects like that. So anyway, tonight he's going to talk to us about things that go bump in the night. So come, I'll introduce our speaker.
Thank you.
You don't need this, right?
I think I'm mic'd already. Yep,
Okay.
I am. And I like getting engaged with the crowd, so I'm going to come on down here, but bring my water. Good evening. Good evening. Thanks for coming out for science on a Thursday night? Yeah. Wonderful. And then thanks to the sponsors of the Vernon Lecture for having me here. It's my first trip to Delaware. I grew up in Rhode Island, so I've got small state anxiety, but I've gotten over it since living in California since the early 90s, as you just heard. So can you turn down the lights, most of the lights, please? Oh, yeah, great. That'll make it a little bit easier to see. Those of you that are in the back left corner, I fear there's going to be a few slides you'll have a tough time seeing. So if you want to move closer, you might do it now. I dissect the universe. I study gas in and around and in between galaxies. That's my science. But tonight I'm actually talking a bit about the things I do. I use things that go bump in the night to do that kind of science. But for you, I'm going to describe some exotic phenomena that we've discovered in the universe and a bit of how they work and a bit of why we care from them. It's a dynamical sky that I'll be discussing, but for most of us, when we think of the night sky, we think of a pretty static night sky. So how many of you look out at the sky from time to time? Wonderful. I hear it's not been so clear of late, but I'm sure you'll have another opportunity. Maybe tonight. Was it clear? It was kind of clear when I came in. Is it clear out there? No? Oh, well. Here's the night sky from the desert in San Diego, and Zabrega Desert. And when I think of the night sky, I think of it as pretty static. And by static, I mean largely unchanging from night to night, other than its movement across the sky, thanks to the rotation of the Earth. Very beautiful, but largely unchanging. And you might think that's because of our limited ability to see the night sky with our eyeballs. But this holds true even when we take images of the night sky with our most powerful facilities. This is an image from the James Webb Space Telescope, which I suspect most of you have heard about, our newest, biggest, most expensive toy in space. And even in the deepest images that we can obtain with the James Webb Space Telescope, the sky here is also largely unchanging. The galaxies, the stars that are pictured on a human lifetime, it's rare that we see much evolution. Which isn't a bad thing. We use the static sky to learn all sorts of things about astronomy. We learn about stars one by one, or at the millions, or in a galaxy at the billions of levels. Or we learn about galaxies, again, one by one, or at the tens, or even these days at the billions at a time analyses. And we take images of other static phenomena. This is one of my favorite images taken of the night sky. This is an image we took, our collaboration of a hydrogen nebula. This is hydrogen gas in the distant universe. And the scale here is 1 million light years across. There's a galaxy here and a galaxy there, and that's 1 million light years. And this is a phenomenal blob. In fact, we call it the slug, given my Santa Cruz affiliation. Go Bears. The slug nebula, this is a diffuse blob, slug of hydrogen gas, connecting several galaxies and fueling the galaxies, the stars that are forming within these galaxies in the early universe. The static sky is also useful to humans. We use it for navigation, both from boats and even from airplanes. So it serves many purposes, but the focus tonight will be on some of the phenomena that do change in our night sky. As time permits, I'll go through all three of these somewhat interesting, maybe even exotic phenomena, probably ordered in degree of weirdness. And we'll start with supernova, which presumably most of you have heard about. And to motivate my discussion of supernova, let's start here on Earth. As I stand here, there's a 1g of gravity, the gravitational force of Earth we often refer to as 1g. That's an acceleration, but call it a force as well. There's 1g of gravity all on the surface of Earth everywhere as you travel across Earth. Why doesn't it collapse? This is going to be an interactive talk, by the way. This one's easy, perhaps, right? We're all comfortable with solids, or even the difficult it is to compress liquids. So it's electromagnetism. It's the fact that solids have crystal bonds that prevent compression and prevent the collapse of the Earth, thankfully. All right, fine. Now think about the sun. The sun is a massive ball of gas, mainly hydrogen gas, and is about 300,000 times the Earth's mass, which on its surface means it has 30 Gs of gravity. All right. Why doesn't it collapse? Oh. And then there are even more massive stars. Betelgeuse, which is towards the center of Orion's belt, if you know your constellations, and poised to perhaps die any moment now, is 3 million Earths worth of mass. Why doesn't it collapse? So I heard some suggestions over here. I'm happy to take one. You can raise your hand or shout it out. Thermal energy. Yeah, and what does that thermal energy do? It fights gravity. It leads to a pressure. I heard someone even say the word pressure. We're familiar with heating up gases, steam in particular, and when you do so, it generates a pressure. And that pressure balances in the sun, or in Betelgeuse, balances the gravitational force of that mass. Great. That's how stars survive for billions of years without collapsing. Why is it hot? There's a source of energy, great. E equals mc squared. That actually plays a role here. Very good. What's the change in mass due to? Nuclear fusion. Very good. So I should have also apologized at the start. I'm not an astronomer. I'm an astrophysicist. And by that I mean I like to think about how things work and why they work. And so I will be digging into some of that as we go. And that's right. So it's nuclear fusion. The source of energy in our stars, that's what defines a star really, is the fact that there's a nuclear fusion process going on deep in the core, the center of the star. We've been working on this process ourselves here on Earth, nuclear fusion, ideally also to become a source of energy for decades now. When I was a student at Princeton, that was already a very active area of research in the plasma physics lab. We can perform fusion, but still today we've yet to figure out how to generate energy out of that process. It requires us to put in energy to do the fusion and not capture any additional energy in the outcome. So here's a periodic chart. Presumably you're all comfortable with that, periodic table, with hydrogen up here on the left, helium on the right, heavier elements as you go into things that get even so heavy that they don't occur naturally in the universe. And by fusion in the sun, that's the binding together or the bringing together, the fusion of two hydrogen nuclei to form helium. That's fusion. And so the sun makes helium. And when it produces helium, it produces energy, heat, and that's the temperature, the pressure that we get to counteract the gravity. That's what the sun will do until it eventually dies. We've got 4 billion years to go, so don't worry about it today. But eventually that will be the end state of our sun, is the generation of helium in its core, depletion of the hydrogen, and it'll run out of energy. Heavier stars like Betelgeuse, more massive stars like Betelgeuse, they burn hydrogen to helium as well, but then there's enough, they have enough mass and enough temperature at the center of their star to go beyond helium and burn helium into carbon, and then carbon into oxygen and neon into silicon, and then eventually silicon into iron. So in the most massive stars in our galaxy, or galaxies beyond our own, this is the process that takes place, this fusion process. And you build up what we say are the lighter elements of the periodic table, the elements up here, beyond helium all the way out to iron. But iron won't burn. You can't burn it at home, you can't burn it in a star. It's not a It's not energetically favorable to turn iron into anything beyond that in the periodic table. So that's the end state for Betelgeuse as well. Or not that is the end state for Betelgeuse. Eventually, it'll burn up to iron and go no further. So what happens when it runs out of fuel? Collapse, that's right. A sad state of affairs. And a sudden state of affairs, we believe, for a star like Betelgeuse. And in that process of collapse, computer models, and we have evidence I'll describe in a minute, indicate that there's a burst of neutrinos. And I'm going to introduce of order 5 or 10, I don't remember how many, terms that you may never heard about or phenomena that you may never heard about. Neutrinos are not something we commonly discuss as humans, but they're all around us. In fact, there are of order billions of neutrinos streaming right through you right now from the sun. They're a bit like electrons, which you know about, but have no charge, have very low mass, travel near the speed of light, and then interact very weakly with anything, including our bodies. They just stream straight through. But these neutrinos generated during the collapse of that massive star do interact with the gas that's collapsing and is expected to lead to an explosion that destroys Earth. Oh my gosh. Perhaps to give credit to whoever designed the movie, that sweeping through with the neutrinos, they're not causing any trouble. Just like on Earth, just like with our bodies, they stream straight through. But that's the end state that we believe for Betelgeuse and massive stars like it. And that is what we refer to as a supernova.
Question.
Please.
Do we know why neutrinos do not interact with much at all? Is it because they're so tiny, or is it?
Their cross-section is extremely low. That's how we would phrase it in physics. Yeah, and that is derivable from first principles of particle physics and then measured in the lab. Yeah. What we didn't know for quite some time is whether it had any mass at all, but that's been proven as well. Tiny, but not zero. Mm-hmm. Ha! Okay. But there'll be bonus questions. Here's an example of discovering a supernova, if you will, in a spiral galaxy not so far away. That explosive event is so bright it far outshines the star that created it. In fact, it outshines any star in that galaxy, obviously. Almost can even outshine the galaxy itself. Not quite. And lasts for days to even years, depending on the type of supernova. Here's one I discovered in the Mount Cuba Observatory today. There's the supernova of this galaxy known as M101, observed with the 24-inch telescope there at the observatory and beautifully displayed in the hall. My photo doesn't do it justice, I'm sorry. It's the best I could do. Here's one that went off during my lifetime. I was going to say during all of our lifetimes, and I just realized how old I was. How many people were not around in 1987? Oh, gosh, yeah. You up here, don't look back there. It's disturbing. Oh, boy. Beautifully named supernova 1987A. We're not so great with naming supernovae. There's the supernova. There's a galaxy, one of our closest neighboring galaxies. I'm going to walk over there for a bit. Who can name that galaxy? Wow, the Large Magellanic Cloud. Very good. The LMC. Who has seen the LMC with their eyeballs? Any human can do it, in principle. Very good. Where were you at when you saw it? You were in Chile. And you? Australia. So it is in the southern sky. Most of us living up here, well, any of us living up here cannot see it. But if you do go to the southern hemisphere, it's bright enough and actually in a position favorable, you can almost see it all year round effectively. It's our nearest neighboring galaxy, one of them. And yeah, in 1987, a supernova went off, which we would consider very close by. We detected the neutrinos from that event, 13 of them. 13.
Who detected?
There's a mine in the Midwest. Ooh, am I going to get the right state? Is it Illinois? I'm going to guess. I forget the name. There were 2 detectors. That was one. That's the United States one. I forget the other one. Yeah, and between the 2, 13. I don't think it was China. I don't know. Homestake is the name of the mine. So with those 13 neutrinos, we largely verified that picture I described to you as well. Here's a view of the supernova today from the James Webb Space Telescope, impacting its surrounding environment. Quite beautiful, and still obviously very easy to observe, at least with that telescope. All right, so that's cool, but so what? Well, the so what for these supernova is back to the periodic table, and my apologies for those of you in the back corner, but I'll read it for you if I can. This is one of my colleagues. We were postdocs together when I was at that Carnegie Institution. Jennifer Johnson, she put together this beautiful version of the periodic table from an astronomer's perspective, and it's color-coded by the process that generates the elements in the periodic table. And so green, that color, that says exploding massive stars, like this Betelgeuse. Green are the elements that are generated by these exploding massive stars. So that nuclear fission we discussed, right, built up elements up to iron, which is here. But even the explosion leads to additional formation of elements a bit beyond that. And so, where is that? Not quite half of the periodic table, but certainly by mass, in terms of the non-hydrogen and non-helium, by mass, that's a pretty dominant aspect of supernovae. Massive star supernovae. Next, somewhat exotic object you may not have heard of, although those of you familiar with Mount Cuba have definitely heard about white dwarfs. These are dead stars, which sounds very depressing, but they're still bright enough, they're still hot enough to be bright and detectable, and they're observed maybe right now in Chile. Are you staring at a white dwarf? Yes, so the object that's being observed, not this one, I don't think, but a dead star. The sun, our sun, we do not believe will explode like Betelgeuse, but its end state will be a white dwarf. These are amazing objects. They have the mass of the sun, but the size of Earth. All right? So because, and again, the sun's 300,000 times the Earth's mass, you've got 300,000 times the gravity. Why don't they collapse? Wow. Electron degeneracy pressure is, and when you hear electrons, you think it's electromagnetism. It's the repulsion of the charges of the electrons. That's not the case. This is a quantum mechanical effect, very peculiar, but again, derivable from equations. Has it been tested in the lab? Probably not. This might be one of the best laboratories of that process in the universe. Anyways, beautiful sources. Some of them have neighbors or companions. Stars often form in pairs, binaries we call them. And that neighbor may still be alive, may still be a star, not a dead star like a white dwarf. And if so, that white dwarf can start eating some of the gases from its neighbor and increase its own mass in the process. We have evidence that this goes on. Yep. Are white dwarfs magnetized? They must have a non-zero magnetic field, but I don't think it's not playing a role in this discussion. These are not magnetars, which will appear at the end if I get there. It's fine. No, please do interrupt and ask questions. If we don't get to the end, that's totally fine.
It's force of gravity that's stealing the
Yes.
gas
just a gravitational pull. The outer layers of a star are weakly bound. I've said 30 Gs or 10 Gs. It sounds like a very strong field, but no, there's enough pull from that white dwarf, which has 300,000 Gs at its surface, yeah, to steal some of the matter, some of the gases away. That degeneracy pressure, as it was called, fails when the mass exceeds 1.4, give or take, sun's worth of mass. And then we expect an explosion to occur. That process is not easy to model. That's not simple equations. But we run computer models. Here's another artist's impression from a computer simulation of a white dwarf on the right, now exploding because it got beyond that 1.4 solar masses and has ignited a thermonuclear reaction and a supernova. Why that you can derive almost from first principles. That's that electron degeneracy pressure fails at that mass, at that gravitational force. Yeah. So, what excites astronomers, one of the things that excites astronomers about white dwarfs exploding is that they should explode around that 1.4 solar masses because that's the limit of the electron pressure. And should therefore have nearly the same explosion and near the same energy, nearly the same brightness, which will figure into why we care about this. So astronomers have been mining for white dwarf supernovae in particular, starting in the early 90s. My observatory, Lick Observatory, which is pictured on the left, got into the game with a telescope called Kate. And here's an example of a white dwarf observed in the outer parts of some beautiful spiral galaxy. Okay, again, cool, but so what? So now a diversion into cosmology. Our universe is expanding, and I suspect most of you have been taught that. And a balloon, blowing up a balloon is a very good analogy, a two-dimensional analogy, but a very good analogy for the expanding universe, where you've got pairs of objects on the balloon expands, those objects move away from each other. Right? And then the part that's a bit subtle, but still I think you can grasp, if I take two objects that are really close together on the balloon and blow it up, they move apart, but not very much. But if I take this object and that object and I blow up the balloon, they really move apart. So objects that are further apart on the balloon move away all the more when I expand the balloon. That's kind of a two-dimensional analogy of the universe. The text just says that. I have to introduce a concept related to that called redshift. This is as deep as I'll get, I think. Redshift is a gauge of that expansion of the universe. It's a stretching of the light here from a galaxy. That's what's being cartooned. We have a galaxy. You see its light. The galaxy is nearby. On that balloon, as it expands, the galaxy moves away from us, and there's a small stretching of the light. If I think of some other galaxy that's farther away, on the balloon, it expands considerably more stretching of the light. So the wavelengths of the lights have been stretched apart. And in particular, some feature, let's call that hydrogen, it's not important what it is, has shifted also towards the red. That's a red shift. And then yet a third galaxy that's yet farther away. Okay, more expansion, more of a shift. And this red shift is gauging that. So Edwin Hubble, about 100 years ago now, demonstrated that the distance to an object of a galaxy, the dots here are galaxies, was proportional to that redshift. The ones that are farther away showed a larger redshift. And this is really the first fundamental evidence that we have an expanding universe. I've described to you a bit about how the redshift works, but not the distance. The redshift is just, let's see how these wavelengths have stretched out and how things have shifted, but not the distance. And for the distance, Hubble used varying stars, again, another hallmark of the Mount Cuba Observatory. One's called Cepheid stars. And let me explain a bit how that works. So how do you measure distance? How do you measure distance?
With the ruler?
With a ruler. How do you measure distance?
Tape measure.
Tape measure. How else do you measure distance? Time. In what? How so?
How long something takes to travel.
Oh, I like that. I heard sound. That's related to the time thing, I think, as well. Any other ways people measure distance? Using a who? A reference point. Ooh, I like that. Yeah, nice. Parallax. Who said parallax? All right. How far away am I from you? 20 feet. How'd you do that? Did you use a reference point? I don't think you did. Well, did you come here earlier and map out the floor and did you use a ruler? Did you use the speed of sound from my voice to your ears? What'd you do? Okay. He's back to the floor. I don't think you did. I think you used parallax. And here's how I would say that. I think, know I'm a human. I am. I have a known size that you're familiar with, right? It's not quite parallax, but it's angles. And as I move further away from you, right, the angle that I'm taking in your field of view is reducing. Each of us have a 360-degree sphere about us. As I go closer to this gentleman, I will take up more and more of that angle in his field of view. So you used angles, which is like a parallax technique. Very well done. That's a technique we use in astronomy as well. Rulers, let's see, pacing it off, but we didn't mention that one. Toys on the golf course. Angles, which is related also to parallax. But astronomers have yet another technique. Yep. Ah. If you go to large enough distances, you need to know the geometry of the universe. Correct. But we do not use parallax. Number one, we don't use parallax to that larger distances.
So Hubble didn't use parallax?
Hubble did, but that's not large enough to matter. At least not much. To go further, we're getting some interference there. Anyways.
But how did he know that?
He didn't. Fine. Sure. And he didn't get it he wasn't very accurate anyway, so. But the linear relationship was accurate. The slope wasn't well measured. Yeah. And I'm just going to punctuate that with, but it turns out the Earth is flat. The Earth is flat. Oh my God. This is being recorded. The Earth is not flat, but the universe is. And so that geometry is not so important here. Yeah. Euclidean, that is. Okay, so the technique that we didn't mention that astronomers are take advantage of and Hubble took advantage of in this case is what we would say use the apparent brightness. If we look at an object that's got a light source, say headlights of a car or maybe better, the house lights of your neighbor. It's pretty rural around here. I was driven around your lovely Newark. Did I get that right? And Wilmington. In between, maybe houses. And some of those areas are far between, but if you can see your neighbor's light, you see it's very faint. And so you know they're not right next to you, they're far away. That's the apparent brightness. Okay. And it turns out objects that are twice as far away are 4 times fainter. And that keeps going. 10 times farther away, 100 times fainter. 1,000 times farther away, 1,000,000 times fainter. So by measuring that apparent brightness, I can estimate how far away a star, in this case, Cepheid star, is from us. But I need to know exactly or approximately how bright that source is. Cepheid stars are great for that. That's what Hubble used because they have a known brightness, which I'm not discussing tonight. And white dwarfs as I just described to you, they explode at about the same mass, we believe. They should have about the same brightness. And so we can use white dwarfs as a way of measuring distances. Okay? See how faint they are, and that tells us how far away they are. That's Cepheids is what Hubble did. Colleagues of mine, by the late 90s, had put together a set of white dwarf observations to do their own Hubble-like law. And I'll show you a plot of that now. Redshift, as I've described to you kind of briefly, but that's the shifting of the light. You can measure that directly. And then the other axis is how bright that supernova is, where the fainter ones are farther away. And what shocked the world, or at least the astronomers, was that this is the line we expected from a, oh, this one's dead. From a ordinary universe, maybe the universe that Hubble envisioned. And yet the data lie on a different line, which is in a universe that is accelerating. So not only are we expanding, but this is evidence, strong evidence, that the universe is actually accelerating in that expansion. And that's led to this crazy concept known as dark energy, which you're welcome to ask me about at the end. I won't have much to say because we have no idea what it is. But it's a leading model, if you will, for what would be this acceleration of the expansion. So that's the why, cool, but why we care about white dwarfs. At least one of the reasons we care about white dwarfs. Part 2, black holes, merging black holes and merging neutron stars. Black hole has 1 quadrillion Gs. 1 quadrillion Gs. This is some illustration of the distortions of light from a galaxy that lies behind a black hole. They range in masses from about our sun to 10 billion suns in one black hole. That's an image from one of the more massive ones, which garnered a lot of attention, as well it should have, from the Event Horizon Telescope. Why doesn't it collapse?
It's already collapsed.
Aha! Very good. Very good. It was a trick question, sorry. The center of our galaxy has a massive black hole in it, about 4 million suns worth. And we know that. One of my colleagues at UCLA, Andrea Ghez in particular, has won the Nobel Prize by mapping the orbits of stars, not planets, but they are orbits of stars around our central black hole, called Sagittarius A. And has precisely measured its mass to 4 million, give or take. But the phenomena of black holes I want to highlight are merging black holes, and ones of less exotic mass, say tens of suns worth of mass. And we've had computer models, well, we've probably had more than, we had probably pen and paper models, but certainly computer models about merging black holes for decades, decades, predicting that they will generate intense gravitational waves. That's what's being illustrated in this kind of schematic. 2 black holes at the center, gravitational waves being emitted as these 2 black holes come in to merge, coalesce. This follows from Einstein's gravity. So Einstein, now over 100 years, formulated a gravity that replaced Newton, basically demonstrated Newton's laws of gravity were incomplete. And one of the predictions of his theory was that sources, even my walking around the room, I believe I'm making gravitational waves. Be careful. They're very weak. At least mine are very weak. I'm not a very big person, and they're very weak to begin with. But if you have exotic phenomena like massive black holes, you generate intense gravitational waves, or maybe intense enough that you have a chance to detect them. So about 30 years ago, we humans decided we had progressed progressed enough technologically to build a detector of gravitational waves. It's called LIGO. This is one of them. And you see these two arms, they're kilometers long each. Inside are lasers that shine on mirrors and measure the positions of objects within the tubes. And by measuring how those objects do or do not move, you can become sensitive to these gravitational waves as they pass through this LIGO detector. Very challenging measurement, 30 years in the making. And in 2015, this was the first detection of gravitational waves by humans. There are two of those two-armed beasts in the United States, separated by thousands of kilometers. And the signal from these merging black holes was detected in each. A bit peculiar, the x-axis shows the arrival time of the phenomena, and the frequency of the phenomena is the y-axis. And you're to be impressed that the signals are very similar. That is, it wasn't some noise in the detector. There's a lot of noise in these detectors, a lot. But these were coincident and same measurements. Cool. All right, but so what? Well, in this case, come on, it's a Nobel Prize. I mean, that's fundamental physics. A prediction 100 years in the making, and finally, with great effort technologically, the ability to detect them. Some of my colleagues, I guess myself included, get really excited by the mergers not of black holes, but of neutron stars. Next weird object here. Neutron stars are like white dwarfs. They're dead stars. And you might be able to guess the pressure here is from neutrons, not electrons. So maybe we should call white dwarfs electron stars. But instead we have here neutron stars. So they're also very dense, about a sun's worth, maybe even a few suns worth of mass. And we have reason to believe some of these may merge from time to time. In 2017, this is the LIGO data of merging stars, this peculiar, what they call them, chirps at the bottom. Lots of other signal, not important. Just showing you the actual data that was the detection. Unlike the black holes, there was predicted the possibility you would see not just the gravitational waves, but other signatures. And by other signatures, we mean ordinary light. And so a postdoc at Santa Cruz was the first human to lay eyes on photons from a gravitational wave source. That's in the black circle as the counterpart, as we call it. So this neutron star merger event not only created the gravitational waves, but enough light to be seen here on Earth with our telescopes. Also emitted in the X-ray, seen with a Chandra telescope. That's the upper right. Also cool, but so what? Well, this is evidence, but I'm not going to call it proof, of the formation channel for the orange elements in this periodic table. So rubidium, gold, and silver. That's cool. Some of the heavier elements, uranium, thorium, are believed, predicted, believe is a funny word, predicted that merging neutron stars are the formation channel for that portion of the periodic table. I say not proof yet because we haven't seen those actual elements in the data, but it's clear we're going to have that opportunity as the years go by. Yes?
When they merge, and LIGO detects that gravitational wave,
Yes?
do you know what pair of neutron stars actually merged?
Do you know the masses of the two neutron stars?
No, not the mass. Which stars merged, or you don't know?
You do not know. You know it occurs right where that yellow dot is, but that galaxy is too far away. Even if we had a beautiful image before the explosion, or the merger, excuse me, we would know nothing about it. The data's not good enough, yeah. There are supernovae that occur very close by. LMC is where you can go and say, look at previous imaging and say, oh, I can infer what kind of star, yeah. But not this, yeah. Maybe someday, but we'll have to get lucky. Yeah. This is quite rare. Supernovae are far more common. Great, and thanks for staying along for the ride. We have the last topic. Hopefully some of you still have the energy. Fast radio bursts. My main astronomical effort these days are on these phenomena, fast radio bursts, which were discovered by an old great technology. This is a 1960s telescope. Hey, that sounds familiar. 1960s observatory, the Parkes telescope in Australia. It's a radio telescope, single dish. And they're wonderful phenomena in many ways, partly the discovery story as well. They were discovered serendipitously. It was an accident. Duncan Lorimer, who you'll see in a moment, was searching for a pulsar, which I'll describe in the next slide, near the LMC, which you've seen earlier in the talk. What's a pulsar? A pulsar is a rotating neutron star, which I just described to you briefly. So they rotate and are magnetized, whoever was asking about that. And they emit a pulse of radio emission they vary, but as short as even milliseconds. So that's what's shown on the right-hand side. So like a lighthouse, as they swing around, you see their light every, say, millisecond with a radio telescope. So that's what he was searching for in this nearby galaxy, and instead found one pulse, and only one. And that was part of the accident. But also, he had made a mistake in his computer program, and if he hadn't, he would have never even seen this object to begin with. So it was truly serendipitous in that sense. He wasn't looking for this, and he screwed up his software. And didn't know about it. He screwed up the software 6 years after he had actually taken the data. So he made the mess up in the software 6 years later, and out popped this. This is on the left is the image of a fast radio burst. You'll forgive me, that's as exciting as it gets. What's plotted here is the arrival time of the radio, photons, the light, versus the frequency of the light. And frequency goes up, with the graph. So that means the lower frequency light arrives later. And if you can't read in the back, that's about a half a second later. So with the radio telescope, you detected the high frequency, and then this sweep, the black line that's curved, is the arrival of the lower frequency photons over about a half a second. And that's Duncan Lorimer who discovered it. We name, like our supernova, we don't name these very creatively. It's the date it arrived. That's a fast radio burst, and this is one of those, where did that come from, moments of astronomy, which is exciting. Totally unanticipated. And that sweep, the arrival time, how long it takes for those later photons to arrive, is about half a second, is actually a count of the amount of matter between us and the FRB. I'm going to start calling them FRBs, fast radio bursts. So how long that light is delayed depends on how much material it had to travel through. Okay, hold that in your head for a minute. That's the why of the story. There is enough energy in some of these fast radio bursts that we detect. We're probably several thousand are probably hitting the Earth a day. Right now we detect about 3 with our telescopes. Some of them are so energetic they would make an entire sun's worth of popcorn. That's the cute analogy in these microwaves. Speaking of which, so they were so bizarre, so unanticipated. For a few years, they weren't even believed. And what didn't help that part of the story was that Parkes was suddenly discovering a bunch of these. And they weren't quite like what Duncan saw. They weren't quite this beautiful sweep, but they weren't so different. And it turned out they were spurious, these other ones. They occurred only at lunchtime. And someone figured out it was when whoever, somebody was going to get their chicken or whatever that is, pizza. They would open the microwave and it would generate a signal very much like what Duncan had found. So that was embarrassing. But Emily Petrov came along with the same telescope and found other signals very much like what he had seen, not so like the microwaves. And also, they took the microwave away and didn't have that issue to worry about. So what makes FRBs? We don't know today. That's part of the fun story of fast radio bursts. I mentioned the word magnetars a while back. Neutron stars again. A magnetar, the phenomenon we think of as scientists, is a rapidly rotating, like the pulsar, neutron star, but even more magnetized, just like a pulsar on steroids. And it's possible the intense magnetic fields around these phenomena create fast radio bursts. Possible. Some of the evidence for that is that we now know some of them repeat. So we don't see just one, I showed you one pulse from a fast radio burst. But some of them, over time, will show not just one, but many. That's what I mean by repeat. Here's the many. Laura Spilker used the Arecibo telescope to show that one of these fast radio bursts not just had one event, but many. That means they're not explosive. They're not dying like a supernova. They're not merging like the black holes and the neutron stars. They must they must persist, and that's partly why magnetars are a favored model.
Is there periodicity in their composition?
Outstanding question. Sometimes. How's that for an answer? This one, which is the first one detected and henceforth has been named the repeater, even though there's now more than one, has hints of periodicity. I'm familiar with one that repeats about every 16 days, but not quite every 16 days. And we use that one for some of our research. Yeah.
Did you and a colleague discover FRB?
So I'm more of an optical astronomer. My colleagues in Australia find the fast radio bursts, and then I go do the parts that are about to come up. Yeah. Unfortunately, this is what Arecibo looks like today. Yeah. Yeah. But now, appreciating that this one repeated, we used a different telescope in New Mexico, a very large array, which is an interferometer. And as an interferometer, you can see there's an array of telescopes. You can even separate them out to kilometers. And it's as if you have a kilometer-sized telescope. But a kilometer-sized telescope were like 80% of the mirrors covered in gunk. But you still got 20% or 10%. And it's a big telescope that lets you pinpoint its location. And so that's what folks did. The square is where the fast radio burst is, both squares. And you can pinpoint down in the sky very precisely. That means we could figure out where this one came from. And it came from a galaxy. We used the Gemini telescope in Hawaii to take an image like that. And so the little faint blob in the circle is a galaxy. And we know that because we use the bigger telescopes, Keck telescopes. Actually, it was the other way around. Keck took the image. Gemini, in this case, took the spectrum. That's the light from a galaxy, trust me. Looks like squiggles to most of you, that's okay. And we could measure its redshift. Oh, we're back to there again. Which indicated it was not so nearby a galaxy, not very far, but somewhat distant from us. So we proved with this source that they're at large distances, not just in the Milky Way, but well beyond. Cool, but so what? This will be our last one. Remind you that arrival time lets us count the amount of matter between us and the event. And that's what really brought me into the field. This is what I work on, actually, more than anything else, the cosmic web. This is a computer simulation of the universe. We astronomers are crazy enough to build models in computers to model the entire universe. That's a bit audacious. When we do, that's what it looks like in the computer. This filamentary structure. Galaxies in this image are the smallest orange dots that you probably can't even see, certainly not the back of the room. The bigger orange blobs are clusters of galaxies. And then you see filaments connecting the galaxies. That's why we call it the cosmic web. This computer model also says most of the matter in the universe is in the bluish regions throughout the image. But that's extremely difficult to detect. In fact, one of my colleagues in Japan wrote a paper saying half the matter in the universe is missing. You can't detect it. We think it's out there, but we have no capability to observe it directly until fast radio bursts. So with fast radio bursts, the radio light from that event goes through the cosmic web, and along the way counts the amount of matter in between us and it. And what in this case we're doing is counting all the hydrogen and helium, which dominates the mass of the universe. So the blue elements which were predominantly formed during the Big Bang. Great, we've hit the end. I've taught you hopefully a bit about things that go bump in the night. There are others, or tidal disruption events. Well, I could probably list another 15 or 20, but these are the fun ones that I get excited about from day to day. Supernovae, emerging black holes, and neutron stars, and especially these days, fast radio bursts. This field is somewhat new, so transient astronomy, while people have been looking at Cepheid stars that you saw for 100 years, supernova, as far as an actual frequent detection, is only maybe 30 years old. LIGO is 2015. Fast radio bursts, it was 2007, the first one, but really only now turning on. And the future is bright for this field because more telescopes are on the way. I'll highlight three, one in kind of each area. The Vera Rubin telescope, which is being built in Chile. It will go operational, actually, I don't know precisely, next year? 6 now? Thank you. Which will detect uncountable numbers of supernova and variable stars and other things that go bump in the night. LIGO continues to have upgrades. Its capabilities are advancing almost by a factor of 2 every few years. That's incredible progress. There's now funded plans to put a device like this in space. I'll probably see that by the end of my days as a scientist. And in the radio regime, the fast radio bursts, actually, there's technologies going on like day by day. A little bit further out into the future will be the construction of a radio telescope that's got a full kilometer of collecting power, square kilometer array, built in South Africa and Australia. And I'm done. Thank you. Thanks for coming. I will take questions.
Was that generated by some kind of tomography type scheme?
I'll repeat the questions. I'm sure you can't hear in the back. I'll paraphrase. How was this visualization of the universe created? So it is a visualization. I'm going to make a guess because I don't know for sure, but what you're seeing visualized primarily is the density. So the output of the computer is what's the density in that location of the cosmic web. And here, I'm sure the darker the hues, the blue, the higher the density. And then they chose orange, I'm sure, for the stellar component, so the kind of stars of a galaxy. Yeah.
Did you have to have multiple FRBs coming from?
To do the experiment, I need many FRBs. Absolutely. One FRB is not enough. Yeah.
When you, the next slide showed the trajectory through
Yeah.
the web. Was your point there that was sort of evidence of dark matter? Because
Oh.
you were, because how that was attenuated didn't account for.
Actually, no, and so let me repeat it. The matter we're detecting with fast radio bursts is ordinary matter, the stuff in periodic table. And by mass, what dominates is hydrogen and helium. So that's why I've circled in the periodic chart, which you may not be able to read, but hydrogen in the upper left, helium in the upper right. And so it's actually electrons that delay the radio signal, but the electrons come from hydrogen and helium, and that's what we're counting up with our experiment.
So
The word invisible is funny. Maybe I should put quotes on there. Too hard to detect.
But isn't that dark matter?
Dark matter is also too hard to detect. So as astronomers, I don't have this. I'll say it this way. I'll just speak it out loud. As astronomers or cosmologists, we've now estimate that the universe is 5% or 4.5% the periodic table, 30% dark matter, don't know what that is. 70% dark energy, really don't know what that is. And then until we did this, and then until we did this experiment, we were missing half of the ordinary matter. That was invisible too. So we couldn't even find the stuff we knew about.
So what are the best hypotheses about dark matter, dark energy?
There are excellent particle theorists that work out gobs of models of what dark matter could be. Okay, there was a prevailing model for the last maybe 10 or 20 years. WIMPs is the acronym, weakly interacting massive particles. We built on Earth detectors to detect particles like that. Nothing. And the next best model is not, is whatever, is 1 of 10 and not within easy grasp of our technology. So at the moment, I won't say it's hopeless, but it's painfully hard. Yeah, yes, sir.
Do you have a scale of the image?
I do. Well, roughly. So galaxies are about 1 million light years apart from one another. So the two, if you can find a pair, you can't see from back here. If you could see a pair of orange dots, that would be a million light years. I bet this isn't quite a gigaparsec, but let's say hundreds of millions of light years. Yeah, probably even close to 500 million. Mm-hmm.
So so that's the map of the universe. If you were to do a just randomly generated map,
Yeah.
and you did a comparison, are there any patterns there, or is this
Oh,
completely
great question.
generated?
Yeah, is this just a random generated field? It does, yeah.
Give me is it the p-score, whatever it is?
Let me rephrase it maybe. Is there information in the topology here?
Yeah.
Or is this a total random Gaussian field?
Yeah, I mean,
Mm-hmm.
if you were to do a random generator field, can you tell a difference between the two?
Yes, you can. So, and part of the reason is there's clustering of the galaxies. The galaxies themselves have gravity that will influence the distribution on smaller scales. But on large scales, it's I can draw a random realization that would be well described by this model.
So there isn't any.
So there's not a scale that is But on smaller scales, things mainly galaxy-galaxy interactions
So there's no
disrupt that.
design you can discern.
Well, there are initial conditions that describe this. How those got there, yeah. Feel free to insert your own.
I'm not adding.
That's okay. Other questions? Anyone on this side of the world? Yes, sir.
So I was wondering, looking at that, does that model this section of the cosmos, or is it another area?
The question is this our universe, as in, is the Milky Way in one of these? So I'll answer it a bit oddly by actually comparing to oceanography a little. It's uncommon in astronomy that we model our universe, like our universe. This is somewhat back to the question that was just asked. We have a random number generator, we make a random universe, and it's got statistically properties like our universe, but our Milky Way is not here. And part of the reason, I guess, maybe when you think about the cosmos, we don't care about the Milky Way. It's one of many galaxies. Whereas in oceanography, we care about our actual ocean, and so oceanographers really do map out their nearby ocean or even the global ocean and use different techniques as a result. Occasionally, people do care about the Milky Way, don't get me wrong, so occasionally we do build a model of a portion of the universe tuned as best we can to match the Milky Way, but this is not one of those. Yeah. Yep.
Way back
That's fine.
cosmic realm anymore
Oh.
exactly, but
Yeah.
Okay, and they're accreting mass from their probably red giant companion.
Good.
And we're now all talking about the recurring nova in Corona Borealis.
Oh boy.
What's the,
You've lost me there, but go ahead.
okay, well, my question is, with a recurring nova, like in those conditions,
Eh.
the whole star, the white dwarf doesn't explode, but the material in the accretion disk does. So what, I guess my question is, what conditions make it such that the white dwarf itself explodes instead of the accretion disk going off?
I got you.
whatever it is?
Yeah, now we're outside my comfort base. Does a white dwarf expert wanna wanna field that one?
The white dwarf explodes when the mass exceeds the ability of the electrons in the plasma to support it. So they have to go faster than the speed of light. And that's where the 1.4 solar masses come in.
Okay.
To support more than that, you have to go faster than the speed of light in anything. So cool. It works.
So the question poses, why do we have these intermediate novae phases?
Accretion disk.
Yeah.
I hate accretion disks. Because we don't understand them. And so you can dump a lot of matter, and the idea is either the accretion disk itself somehow gets hot and goes, or it gets dumped onto the white dwarf a little bit. So there's several different scenarios as to how the nova, the recurring nova occurs.
Okay.
Any nova, actually.
You want to add to that, or?
So basically, the recurring nova are thought to be nuclear explosions, fusion on the surface of the white dwarf. And what happens is that enough material gets compressed onto the white dwarf, it gets hot enough for nuclear fusion to occur, and then it's an explosion. But then more material gets deposited on there, and it can happen over and over again. So it doesn't destroy the white dwarf, it's just a surface phenomena on the white dwarf. But when, as Judy said, you get enough matter up to the white dwarf that it starts to accumulate and it hits this Chandrasekhar limit,
Yep.
then the whole star collapses and explodes and becomes a white dwarf supergroup. So recurring novae are just surface phenomena. White dwarf supernovae are the whole star being destroyed.
Gotcha. Thank you. Thank you all.
You bet. Team effort. Any other questions? I'm going to be happy to stay around as well. But I'll get a new person first. Yeah. Great question. Are they beamed is the lingo we would use. Are radio bursts beamed? There's not evidence that there are. The gamma ray bursts, which I didn't talk about today, I've worked on those too, are beamed. And so we don't think we see many of those, or there's many of those we don't see. But the radio bursts, I don't think there's any evidence they're beamed. Yeah. Cool question. Yeah. Okay, last one.
You would consider this an important question, but
It better, now it's the last one, for sure.
would you be willing to share why
Yeah.
you're moving away from astronomy
Oh.
to astronomy?
I will be glad to answer that one, but that one probably sounds like more of a conversation. So why am I heading to oceanography? The short answer, actually, all right, I will give you a short answer. That paper, I didn't call it to show you a paper, but the measurement of the missing baryons was something I pursued for 20 years. This is embarrassing, with of order $50 million of your tax money, unsuccessfully. I think we did good science anyways, but certainly the proposal was motivated by trying to see these invisible baryons. That project came to a close with this. Close is a funny word, but you get what I mean. And then I had another project going on for 20 years, unrelated, that also roughly completed in 2020. And I love new things, and astronomy, there's new things to do in astronomy, but not for me. So I decided to branch out somewhere else. Yeah. Thank you. And thanks for coming, and thanks to the Vernon family for continuing this lecture series. I'm told, I expect there'll be a fall edition. So come back in around 6 months.